We're very happy to have Karen Crowther here talking about the correspondence principle in quantum gravity.
Great. So
Take it away.
thank you for having me. All right. Of course, the problem of quantum gravity is the problem of finding a theory that, at the very least, describes the phenomena at the intersection of general relativity and quantum field theory. And yet, everything else that the theory may describe, does describe, and even the form of the theory itself are left open, so they're unspecified. And the reason for this is due to the apparent experimental isolation, extreme experimental isolation of the theory. So not only are there no data that the theory is definitely required to explain, but none of the approaches towards the theory have made any unique testable predictions at this stage. So as a result, we don't have a theory of quantum gravity. Instead, we have these many different approaches, each sort of doing different things. Okay, so in the absence of data and predictions, we're relying on principles, theoretical principles. And what principles you want to adopt or view as important will shape the form of your theory. Also, principles standing in to serve to define what may count as success of the theory. So the fulfillment of particular principles may count as an achievement, something to strive towards. Also, principles represent concrete links to established physics. So by this I mean the principles that we are interested in because they come from successful theories. And also, successful theories typically link back to other theories. So, given problems we're having in finding a theory, I thought it might be helpful to go back and look at some of these principles. So today I'm going to be talking about the correspondence principle, which is used in all the approaches to quantum gravity. It serves not only as a heuristic aid to try and develop the theory, but it's also treated as a criterion of theory acceptance. So again, we expect that any successful theory of quantum gravity is going to exhibit correspondence. So the main questions that I'm going to talk about today are why, in both of those roles of correspondence. So how does correspondence serve to aid in theory development? And also, why do we believe that an acceptable theory of quantum gravity must recover general relativity and/or our quantum field theories? And second main question is, what counts as correspondence? What does it mean to recover general relativity? And some other questions that I'll briefly touch on will come up. It's kind of the more general worry, why do we seek to preserve non-fundamental theories? And is the dual role that correspondence is playing here going to be a problem? And what I'll find is that there are lots of different forms of correspondence. There are some that are heuristically valuable in theory development. Others, I'm going to argue, have quite undue weight in quantum gravity research. Within the different approaches, there are different ways of recovering general relativity, and these have varying degrees of strength. But perhaps it's undesirable to go for the really strong one and imagine that quantum gravity must strictly reduce to general relativity in the low energy limit. Okay, so I'm going to start by explaining what the correspondence principle is. I'm going to talk a bit about its heuristic role, the role it plays in explanation, before finally getting to correspondence in quantum gravity. So I guess most of the interesting stuff might be in there. So, can you speak? Oh, sorry, it's my throat. So the generalized correspondence principle, it states that any new theory, we'll call L, must account for the success of its predecessor, S, by having some of its laws approximate those of S in the domains where S is known to be successful. Of course, a familiar example is special relativity, reducing to Newtonian mechanics for low velocities. So the generalized correspondence principle obviously comes from Bohr's correspondence principle in quantum mechanics. But actually, what we now think of as Bohr's correspondence principle is not what Bohr himself meant by it. Ooh. Am I still there?
Yep.
So actually, Bohr discovered several different relations between quantum and classical theory. And it's not clear which one of these that he meant to designate the correspondence principle. But whatever he meant, it's clear that he didn't mean it to be what we now know as the correspondence principle, this kind of general idea that quantum mechanics will go over to classical mechanics in the realm of large orbits and large masses. So his student Rosenfeld questioned him about this, and Bohr says, nope, that's not the correspondence argument. The requirement that the quantum theory should go over to the classical description is not at all a principle, it's an obvious requirement for the theory. Ooh, have to excuse me for a moment. Okay. And the problem we have today is not dissimilar. We've got many different relations that we designate the generalized correspondence principle. So Stefan Hartmann, in reviewing kind of this large edited collection, identifies seven. Wait, where am I? Sorry. I think it's not.
Oh, sorry. Go for it.
There we go. 7 different relations. I'm not going to go through all of them today. The ones that I think are interesting for our purposes are numerical correspondence, where S, the old theory, and L, the new theory, agree on numerical values of some quantities. Observational correspondence, which is kind of the quantitative version of this, that L degenerates into what we are expected to observe according to the old theory. And also law correspondence, where laws from the old theory also appear in the new theory. But given all these different relations, there are some general messages across the whole lot. Firstly, and these are from Rada. So firstly, the theories, they have to match up in the same domain to have correspondence. So even though the theories will likely have different domains, they have to intersect somewhere. And it's in this regime that we expect correspondence. So in other words, the two theories have to agree on some of the same phenomena. Apply to some of the same phenomena, and it's here that we want correspondence. And secondly, the two theories are often incompatible. So typically a straightforward deduction of the old theory from the new theory, it's not possible. So we employ these idealizations, approximations, meta-level arguments. Most familiar of these, of course, are limiting relations involving the characteristic constants of the new theory taken to a limit whereby they become invisible by the lights of the old theory. But these aren't involved in all correspondence relations. We don't necessarily need a limit. So the third general point worth noting here is that correspondence is not between entire theories. So not all equations, predictions, and laws in L are going to correspond to some in S, and vice versa. So in the first case, where not all of the stuff in the new theory corresponds to stuff in the old theory, this is obviously because this is a new theory. It's predicting new stuff, and we expect it to have a broader domain of applicability than the old theory. But in the second case, where not all of the insights of the older theory are preserved by the newer theory, this is what some authors have called Kuhn losses. And it's worth noting this is going to be true even if we restrict the old theory to just the parts that were responsible for its success, so the explanatory core of the theory. Okay, so yes, general correspondence principle, like I said, it plays these two different roles. So firstly, it's used heuristically in the development of the theory, or discovery of the theory, but then it's also used kind of as this criterion of theory acceptance. Once we have the theory, we then kind of appeal to this correspondence in order to justify our use of it. So Ratter kind of attributes this kind of sharp distinction between the two to the legacy of Popper, and his belief that the data, principles, etc. used in constructing the theory can't then be used later on, again, in its later justification. But then he argues that, well, actually, this can't be true because there's no well-defined stages that we call theory construction and then theory justification once it's been developed. Instead, he claims that theory development is a continuing process, and both of these roles are being used in this way throughout the theory development. So I think this seems to be what's happening in quantum gravity as well. Okay, so we've seen that the generalized correspondence principle is not well defined. Instead, it refers to numerous different relations. So me today, I'm not going to seek a general definition that covers all of these. I'm just going to instead use correspondence to refer to any of these relations, any and all of these relations. And then the generalized correspondence principle, as I use it today, is the principle stating that the new theory has to stand in at least one of these relations to its predecessor, S. Okay, so more about correspondence. So we typically think of correspondence going from the new theory back to the old theory. The new theory should satisfy the constraints presented by the old theory. But it's worth noting that we also use it the other way, especially in theory development, as a way of kind of, exploring the interrelations of our current physics in order to learn something about the structure of the new theory. And I think because of this, the way it's used from the old theory, exploratory, looking for the new theory, this part is not always going to strictly match up to these definitions of law correspondence, mathematical, numerical correspondence, etc. Because these ones typically make sense only once you've got a mature enough theory that you can then go back and, formally write these out. So I want to emphasize that there are forms of correspondence that are explicitly heuristic and kind of exploratory or working correspondences rather than formal relations, during the process of theory development. They're not the ones that are going to be necessarily enshrined in the textbooks later. So, obviously there are a lot of examples in quantum theory. Some forms of correspondence in quantum theory don't hold because of the measurement problem. But there are a variety of other ones that do. As an example, we can go from quantum mechanics to classical. There are numerical correspondences that we arrive at by physically specifying these limit domains, whereby h is taken to 0. example of Coulomb scattering here, where this corresponds to the domain of small scattering angles, and we have numerical correspondence between the two frameworks in this small differential cross-section. So these are straight out of our writing paper. So another example going the other way, from the old theory to, quantum mechanics, classical mechanics, turning classical theories into quantum theories. I guess I don't need to go through all this, but it's this rule of transforming classical equations into quantum ones by formally replacing classical quantities with corresponding operators, and then having the numerical values of the classical quantities correspond to the eigenvalues of the eigenvectors for the corresponding operators. It's worth noting, though, that this rule doesn't work by itself. We need to use these supplementary assumptions, which we justify either by the fact that they lead to successful predictions or theoretical considerations such as symmetry. Also, we can't produce the whole of quantum theory, only those quantities and expressions for which a classical analogue exists. A bit tautologist there. Okay, so generalized correspondence principle, it finds widespread application in science, particularly this big edited collection that I spoke of before, a multitude of case studies. And again, in many cases, correspondence is only demonstrated once we have a sufficiently mature theory, so post hoc after theory construction. Because of this, some authors have kind of questioned its heuristic value in developing the theory. But as I've already began to argue, I think if we view correspondence as important after theory construction, then surely it's something that's important at any stage. So even if the textbook enshrined version is only going to come later on, I think we can and do still work towards correspondence. And I think we're capable of reasonably judging theory's prospects, kind of hitting these constraints, while recognizing that these might not be the final ones. These are all tentative assessments. So, oh, did I move down? You lost me.
There you go.
Okay. So, sorry, it's a bit small, but for this reason, I claim that Hartmann is incorrect when he claims that mathematical and law correspondence are of low heuristic value. These types of correspondences played a significant role in the development of quantum theory, working towards numerical correspondence, led people to investigate the relations between the mathematical objects in both theories, and certainly useful in theory development. So, but again, they don't strictly match up to these definitions that he's provided because they're working correspondences. So, I maintain that although generalized correspondence principle provides neither a definite set of rules to follow in theory construction, and nor does it provide an exact criterion for theory acceptance, this kind of general striving we have to have the new theory make connections with existing physics is a useful heuristic strategy. And as well, successful theories typically exemplify some form of correspondence. So in this way, I think it's similar to the principle of unification, which also serves as an objective in theory construction, but not well defined. The theories that do, we claim that unified theories, different things going on. Okay, so, and yet it's not the success of the principle that is typically cited as the reason why we want correspondence. It's its role in explanation. So, of course, there's this expectation that the new theory should explain why the old theory, which is false, by the lights of the new theory, why it was so successful in spite of not being correct in the light of the new theory. So, I don't know, I kind of find this a strange idea. They're kind of justifying our continued use of the old theory. That correspondence is as much, well, maybe not as much, but a large part of it is about explaining the old theory as well as the new theory. So, yeah, I think that's interesting. But the other reason why we want correspondence, of course, is because in order to accept the new theory, it's got to somehow go beyond the old theory. It's going to be inadequate as a replacement if it doesn't at least explain what the older theory has explained. So there's this idea that we believe the new theory should not render inexplicable any phenomena which are already explained by the older theory. So because of these two aspects, I think correspondence is mostly about kind of easing our conceptual tensions. But that's something I'd like to discuss here. So the reason, obviously, correspondence relations, we've got so many different ones, and many of them aren't strictly formal derivations. So because we've got such a range of relations, I think it's a legitimate question to ask whether these all do the job of explaining the success of the older theory, or proving that the new theory is at least as successful as the old one in describing the same phenomenon. Okay, also I want to argue that the type of explanation provided by correspondence is not necessarily conceptually satisfying. Obviously, the relations between quantum and classical theories fail to be explanatory in a crucial respect thanks to the measurement problem. And, sorry, that should be if. If quantum gravity doesn't solve the measurement problem, I think it's also going to fail to be explanatory in this respect. So, if quantum gravity tells us that the micro degrees of freedom of space-time are quantum entities, then we need an explanation of the large-scale classical appearance of space-time. And I believe that invoking external hypotheses such as decoherence are not going to help with this, given that quantum gravity is supposed to be a fundamental theory. I think the explanation is going to have to come from the theory itself. Oh, excuse me again.
It's a whole box over there if you want.
Okay.
If you need it.
All right, finally at quantum gravity. So, thank you. So, quantum gravity correspondence is used in both directions. So, obviously as a criterion of theory acceptance, the recovery of general relativity is viewed as an essential constraint on quantum gravity. For a theory to be accepted as quantum gravity, we expect it to recover general relativity, though it's not, clear at that stage what that means. But it's also used heuristically from general relativity and our current theories, kind of explore their relations and learn something of the structure of quantum gravity. So, and I think this is kind of a unique problem to quantum gravity, where these two roles come together. Because of this experimental isolation. So we're looking to replace general relativity, but the only empirical data that we have to guide theory construction are already all explained by our current theories. So I'll come back to that point. Okay, so from S to L, so the old theory, to quantum gravity. We're exploring the limitations of general relativity and the consequences of combining it with quantum theory. And I think this plays a huge role in quantum gravity because it clarifies but even defines the very reason why we're looking for a theory of quantum gravity in the first place. So there are several different approaches, semi-classical theories, though there are some of these that go the other direction. Quantum field theory in curved space-time, the treatment of general relativity in the framework of effective field theory, and also quantizations of general relativity. So one of the big results of this kind of exploration is the expectation that quantum gravity describes physics at the Planck scale. This obviously follows from dimensional analysis using the constants of our current theories. So semi-classical approaches couple classical gravitational field with quantized matter energy. These sorts of theories, and they're exploratory. They're supposed to reproduce the results, so observational or numerical correspondence of quantum gravity at low energy scales. So in this way, I see them more as like stepping stones towards a theory rather than representing full theories themselves. Okay. Another approach is quantum field theory in curved space-time, which describes how gravity affects quantum fields. And exploring our quantum field theories in the regions of black holes have led to a lot of important results, such as Hawking radiation and Bekenstein entropy, that are now serving as kind of the data for quantum gravity. So we expect any theory of quantum gravity to now explain these results. And interestingly, exploring our current theories and their kind of interrelations and pushing them and their limits this way, we've found additional correspondence in terms of black hole thermodynamics, analogous to classical thermodynamics. Okay. And then, of course, another way of going from our current theories to search for quantum gravity is by quantizing GR. Two different ways of going about this, covariant and canonical approaches. Both of these involve kind of recasting general relativity in a form suitable for quantization. But doing this, we're sacrificing particular features of general relativity. For example, these perturbative methods in covariant quantization result in a theory that's no longer a theory about curved space-time, and the association between gravity and space-time gets lost. So I think issues like this really prompt us to reflect what aspects of general relativity we really value, like which ones represent fundamental conceptual insight or embody essential theoretical virtues that we necessarily want them retained in the new theory. And interestingly, if these are to be retained, in what form? Are they going to look like the usual principles and relationships in general relativity? I think if they're something very different, then we're going to expect some sort of correspondence relations between the new version and the old version. So I think these are interesting questions. Okay, so the other way around now, from our approaches to quantum gravity, trying to link back up to our current theories. This way of using correspondence is kind of less heuristic and more about theory justification. of course, that quantum gravity recover general relativity. We view it as a essential part of what makes a successful theory. And yet, given this kind of prominent role that it plays, unfortunately, it's totally unclear what this would entail. So string theory, I think, has been the most successful in this regard. So people have hailed it for its claim to contain or predict gravity. And this is because the graviton appears automatically as a quantum vibrational mode in the string spectrum. But the superstring spectrum also contains a lot of other vibrational modes corresponding to, all our known fundamental particles and forces. So it also exhibits correspondence with the standard model. So the low energy effective field theory that we construct from string theory contains the same objects that we interpret as representing particles and forces in our current quantum field theories. But the way in which it does this, I think, is not straightforwardly linking back to general relativity or making these kind of conceptually satisfying aspects. But of course, string theories will debate this. And here I'm really hoping that I'm right. So of course, there's another form of correspondence in string theory, and that is in order for the theory to be well defined. The background spacetime must satisfy the central equations of general relativity, being the Einstein field equations. So Nick argues that the background metric field is composed of stringy excitations, and it's to be identified with the gravitational field. So claims that general relativity is a low energy effective theory of strings. But yeah, I'm not sure on that point whether we would call that a derivation of the Einstein field equations or not. Instead, it seems that we're identifying structures in string theory with space-time in general relativity. Okay, so other approaches? Obviously much less complete. They've also had less success than string theory in this regard. So loop quantum gravity, causal set theory, causal dynamical triangulations. Again, they're kind of constructed from our current theories, so going from S to L, but they're all having trouble going back the other way and making links with current physics. In loop quantum gravity, we've got difficulty in finding the low energy limit at all. In causal set theory, there's this inverse problem where there's no dynamics for the growing causal sets that correspond to manifold lax spacetimes. Causal dynamical triangulations has had some success. It's managed to recover the correct spacetime dimension according to general relativity. So also we have theories that are not approaches to quantum gravity, not considered approaches to quantum gravity, but they managed to demonstrate correspondence with general relativity, which I find very interesting. Sakharov's kind of induced gravity program. He shows that quantum field theory on a Lorentzian space-time, the effective action that we get at the one loop level automatically contains terms proportional to the cosmological constant and the Einstein-Hilbert action of general relativity. Also, we've got these condensed matter models of black holes that reproduce at low energies an effective space-time metric, the same as general relativity. Again. Okay. So, yeah, somehow I put, saying to you yesterday, Nick, I put all my philosophical points in the conclusion, so here we go.
I think you've been provocative enough.
Oh, that's good.
Already.
There's hints of what I'm going to say. So, obviously the heuristic role of correspondence, from the old theory to quantum gravity, I think is responsible almost exclusively for shaping what quantum gravity will look like, the regimes where we expect it to apply, and I think essentially these kind of problems that come from combining our current theories seem to be the reason why we're seeking a theory, well, the main reason why we're seeking a theory. But also our current theories provide the data for quantum gravity. Of course, the example of the Bekenstein-Hawking entropy, where this is a target that we're taking quantum gravity to reproduce. It's not itself an empirical result. So I think the most difficult aspect of correspondence from S to L is kind of figuring out which parts of our current theories kind of serve different roles. So they might be heuristically useful in kind of a search for a theory, but then aren't themselves retained in the actual theory. Other aspects will be retained, but in what form? And again, if it's something radically different, then we're going to expect correspondence. Okay. Going the other way, though, I think kind of trying to link back to general relativity, I think it's acquired a status of undue weight in quantum gravity research. So there's two reasons for this. Kind of one, the experimental isolation of the theory, but also one of the expected roles of quantum gravity is to be a micro description of space-time and kind of explain general relativity. So because of this, I think correspondence has, been treating like a prediction. Particularly in string theory, a number of people have claimed that gravity is a prediction of string theory. But I think this also happens in the so-called discrete approaches, which seem to take the recovery of space-time as one of their main goals. So we've got to be careful here. It can't fulfill the role of prediction. It's not a prediction. Again, we can recover gravity even from theories that we don't consider approaches to quantum gravity. So correspondence is not sufficient in itself for a theory. It's got to do more than just be a micro description of space-time to explain gravity. So of course the main aim that we need to remember is that we want a theory that describes phenomena at the intersection of general relativity and quantum field theory. And obviously one of these intersections is the Planck scale. So I think these two ideas have become tangled up because obviously one of the ways to kind of that we could possibly get testable predictions from quantum gravity is arriving at a low energy limit. And if this low energy limit is just general relativity, then we can see how we've confused it for a prediction. So I think actually taking this kind of really close recovery of general relativity, it might prevent us from making genuine predictions in this regime. Obviously, we don't want to conflict with the results of quantum gravity, general relativity. But I don't know, I think there's space to have the theory say something kind of outside of the domains that general relativity that we know it applies to. So I want to emphasize this distinction between the idea of a low energy limit and correspondence. They are two distinct ideas. Okay, so seeing correspondence need not be a limiting relation, and it need not mean that all the laws of the new theory strictly reduce to those of the old theory. We can have correspondence without totally reproducing general relativity. So I think maybe, this is a bit sketchy, this claim, but the difficulties that some quantum gravity approaches have with recovering spacetime, while these may be symptoms of their incompleteness, it might also be possible that they're indicating something interesting. So to try and force them into correspondence might be a mistake. Okay, whoops. Wait, is that right? Yeah. So again, to conclude, we've got these working correspondences that are definitely useful in searching for a theory. But we recognize that these might not, well, yeah, probably not, I don't know. They won't be the final form that is enshrined in the textbooks, so don't go looking for that. So I think also that correspondence relations by themselves are unlikely to explain the classical appearance of space-time. The theory itself needs to do this. Yeah, supplementary hypothesis? Yeah, if you consider quantum gravity fundamental, I think actually invoking these supplementary hypotheses might not be conceptually satisfying either. So I'll fix that. Okay, and finally, suggestions for future work. I think we could use a detailed exploration of these different correspondence relations and their roles. Firstly, to determine if the success of the principle is due to a particular feature of these relations, but also to potentially develop correspondence into a more useful criterion. Okay, thank you.
I'm unclear how exactly the insufficiency of recovering GR or gravity somehow from the fundamental theory is supposed to show that the correspondence from L to S is misguided, or has given sort of an undue weight, because it seems to me it's still obviously going to be a necessary condition, even though of course not a sufficient condition on any of these fundamental theories. Now, I mean, having said that, I agree with you that particularly in string theory there's this misrepresentation or maybe this sort of running together of prediction with correspondence or with a low energy limit. I think you're quite right to say that this is not a prediction, or at least not a prediction as it's usually understood. Mm-hmm. So I agree with that, but if you take away the rhetoric of the prediction and you just think of establishing a correspondence back to GR as a necessary constraint on any fundamental theory, how can the insufficiency of that speak against its necessity?
I guess I wanted to kind of raise the question of why we think it's a necessary condition on quantum gravity. And I think it has become this way because of the expected role of quantum gravity, which comes from correspondence the other way, like I was saying, to be a micro description of space-time. So I think you're just taking that as a definition of the theory. So I'm really just trying to have us go back and think about why do we take this to be. So particularly when there are so many different forms and ways that we can link back to general relativity. Which one of these is the necessary one? Just any of them? I don't know.
I guess my question next. Sorry, there's feedback loops in there. Sorry. So I think my question connects back to the more general point you made, where you said that you find it a somewhat strange idea that a new theory has to explain the successes of the old theory, and I, on the other hand, find it strange to think of this as a strange idea. I think it's the most natural thing, because, I mean, after all, we know that the old theory has been successful to the extent to which it has been successful in accounting for certain things. So clearly, if we can't connect back to that, then by virtue of with what justification could we replace that theory with the new theory? I mean, can you explain why you find this strange as an idea?
That we're replacing a theory, so we view it as inadequate in some respect. So why do we think that's unique? I guess this comes down to a question of underdetermination. Why should this kind of patch of theoretical space that we've hooked onto? I think we're just kind of using correspondence in this way to ease our conceptual tensions. Kind of we want our theories explained. We want expect this coherent picture of physics. So I guess the point I want to make is, do these different relations, do they all do the job of actually linking back to general relativity in such a way that all its insights are preserved? So is there this strict derivation? And I kind of think no. There's just a way of showing, there's the link here, but I don't think that link in itself is going to get you everything you want. I think it's just a way of justifying our continued use of the theory where it works, obviously. It might be like a shorthand, a trick way of getting numerical correspondence, which I think is really what we want, especially if the new theory contains new conceptual insights.
Okay, but you agree that at least something like numerical correspondence is a justifiable, necessary condition sort of on the new theory? Certainly the new theory should not contradict results that we know hold. But the way in which it approximates them, I think, is open. So, numerical correspondence in that respect, of course. But I think we have to think, the new theory can, and we want it to kind of go beyond that. And it may reveal links between things that we didn't previously consider to be gravitational phenomena. Okay. Other questions? No?
I'm going to let Queso ask a question.
Has another question.
I still have to think about it for a moment, so
Okay.
let me go on push card. Absolutely.
Did you hear that, Nick?
No. I
So
suspect you're
Julius needs a few more minutes to articulate his question.
Okay. And then he'll have to do it louder as well. So we'll ask Keizo a question. I'll let Keizo ask.
A question, yeah. You mentioned something about thinking that quantum gravity will have to solve the measurement problem. And I wonder if you could kind of discuss that a little bit more, because as it is now, it tends to be the case that people who discuss the measurement problem and interpretations of quantum mechanics and whatever we want to call it, these are done completely in isolation from questions of quantum gravity. And many of these people would probably say something like, well, maybe we can solve this separately and the quantum gravity will still be kind of a quantum theory, so why can't we just export it like kind of, okay, we have our solution for quantum theory here, let's just apply that to quantum gravity, whatever that is. So why do you think that quantum gravity will kind of play a more kind of important part of developing the kind of discussion of measurement problem? And do you think that we should try to kind of be more of a connection between these people debating the measurement problem and people who reflect upon quantum gravity?
Yeah, that's a good question. It's really interesting. So I guess I've got a few things to say. Oh no, I should have been taking notes. So I guess firstly, it's interesting how, Chris is so insistent that we recover the insights of strictly derive general relativity, and we don't kind of have this same idea about recovering quantum mechanics or explaining quantum mechanics. Like, is that? I think that's interesting. So I think if we were to kind of, but then it's I guess a different point whether in order to explain quantum mechanics you need to solve the measurement problem. But I guess the point is, if you were to just assume quantum mechanics rather than try to explain it, I don't think you're going to have a conceptually satisfying fundamental theory. So the reason for kind of wanting to solve the measurement problem is, I think, again, just to have something explanatory, conceptually satisfying, which I think is it's kind of the weight people are putting on quantum gravity. People want it to do a lot of stuff, even though not much work has been done on those things. Like, we're expecting a more fundamental theory in order to explain, dark energy and dark matter and all this, and is quantum gravity going to be it? I don't know.
Okay. So I'm going to ask my question and give Julius a little more time to perfectly frame his. So I want to push, obviously, I want to push back a bit on. I actually want to say first, I thought this was really great. There's some things that Chris and I have been talking about, physical salience, and maybe we'll circle back to those that I think tie in very much to some of the things.
Yeah, in the paper I talk about
you were saying here. But I want to push back about quantum gravity. I guess I'll send you the chapter from the book so you can sort of see, PSA made us write something really short there, so there's a lot kind of missing there. So we probably did talk about it in terms of a sort of low energy limit, and I probably do still in the chapter, but it's more accurate to say that this is a result that has to do with the first order of perturbation theory. That's, you look at the lowest order of perturbation theory, and that's when you get at that level you get the constraint on the background fields, the Einstein field equations.
So there is space for other stuff to
Yes,
happen.
so absolutely, if you go to higher order, you're going to get quantum corrections to the Einstein field equations. So it's absolutely not a kind of recovering of exactly GR.
Yep.
Does that make you feel better about it? Does that answer some of the criticisms that were there?
I guess it's kind of I kind of knew that when I was writing this. Like, we still have all these different correspondence relations in quantum gravity. I'm not sure people are actually seeking a strict derivation. Well, at least none have popped up, but whether they're looking for them. Yes, I guess. Yeah, my point is just to not think of it in that way. Like, be more consistent with what's actually happening. Yeah.
So I think I had this, if I heard Chris's question right, the same sort of inclination. I mean, the whole point here is not because GR's up on a pedestal, but the GR gets so much right, experimentally.
Oh, of course.
And the route to getting that back is, rather than doing it piecemeal, sort of prediction by prediction of GR.
Yeah, it's a shortcut.
Try and find some cases, some limits, some cases in which GR is going to be recovered, and all the empirical successes are going to be covered in that sort of case.
So that's it. I think we have to recognise that that's what's actually happening, and that's what we need to strive for. We don't need something stronger than that.
Since I've got your attention, we're talking about this thing. There was another kind of point in one of the slides at the end where, you commented on the argument that Tiziana and I kind of gave or reported.
I should have checked that with you before I talked about it. I knew.
No, but then we have a more fun kind of. No, this is great.
This is talking about.
That's perfect because we're going to record it and then the discussion will be online and people, that's the whole point of these. Okay. What did you mean? Why didn't you think what was sort of missing from the where you say the background fields are really kind of a certain kind of excitation of the
No, I think
stream field stream?
I think that's all right. I think I was just talking about the correspondence you have. So I wanted to. That's it. I don't know whether you imagine this to be a derivation. I'm not sure you do. So for people who think that quantum gravity has to derive general relativity, I'm not sure this counts as a derivation in that sense. But instead we've got this nice relation where you identify the structures in string theory with those of general relativity. So that's the form of correspondence.
Okay. Yeah, no, I totally agree with that. And actually, this won't mean anything to anybody else, but the last slide I had on my talk at Notre Dame about non-commutative geometry, I think it's probably the same kind of point you're making. In the derivation, when you're going from something sort of non-spatio-temporal or rather different to something that is, there's going to be this bit where you just say, that's the gravitational field, or that's the space-time.
Yeah.
You seem to now you were pushing back a bit on that at the end. That I think in the last slide there was something about. The last slide. That was the supplementary hypotheses. But maybe that's a supplementary hypothesis that this stringy structure is space-time. This non-commutative geometrical structure is space-time.
Yeah, I think I need to delete that line, which I realized during the talk. But I think, because like I said, correspondence does itself involve, approximations and heuristic arguments in this way that aren't coming from the theories themselves. So I think that can be lumped in with the correspondence relation. So I guess I was saying there that the correspondence relation itself is not going to be explanatory.
So it wasn't written in the slide, but I thought I heard in what you say a little skepticism about supplementary hypotheses. What are you kind of saying they may be okay?
I think they're necessary as part of correspondence. But the way in which we're kind of using them or invoking them, I question the way in which that's explanatory. Right.
So, and I'm really abusing my privileges, but this sort of fits together in my mind in such a kind of what we've just been talking about in a kind of logical way. So I think I really agree with that. This finding the the supplementary hypotheses that we find explanatory, I think, is what I don't want to. Chris can say whether he kind of agrees, but I know he's sort of sympathetic at least to what gets kind of lumped under the heading of sort of physical salience here. I mean, which of the explanatory principles are the ones that are acceptable? And then, okay, well, I mean, I think that I totally agree. And I think you've done a very nice job of sort of pointing to this question that they can't just be any old. I think what you're saying is, right, they can't just be any old sort of ad hoc thing.
Right.
So what are these physical principles of physical salience, and how can we tell which are good ones and not? Something, so I come up, and I think the things you mentioned, like approximations and symmetries and other kinds of principles fall under this heading. Somehow, those principles have to, I don't know, the best I can come up with is that so they have to be systematic, not ad hoc, but they have to apply in a lot of different cases.
Yeah.
Something like that.
I guess that's exactly what I'm interested in now. Like the rest of this project is going to be able to go out and now consider some of these principles themselves and their physical salience, the reasons why we're holding on to them, and again in what form, I think is the interesting question. Like they might not be, how they get translated in quantum gravity, I think is interesting.
You should go to Geneva and work with Chris.
Great idea.
Okay, I'm done. You're up, Julian.
Oh, thanks, Nick.
Yeah.
So, can Julius jump in?
Yep, please.
So I guess I wanted to argue that there are some interesting senses in which recovery of spacetime can actually be treated as a prediction of a more fundamental theory.
Okay.
Which kind of, I think the example is not exactly, it doesn't exactly go against what you said, but I think it's related. So I imagine a situation in which I have a fundamental theory which tells me that, which recovers some set of GR spacetime in some sort of limit or whatever, but not all of those spacetimes. So let's take causal set theory as an example. I think one could argue that, in a sense, this theory assumes that there are no closed time-like curves, for example, because spacetime is presented as a partial order, and so on. Now, imagine that we are in a situation in which it turns out that actually there exist closed time-like curves in the actual universe, that something like a time machine can be realized in the universe. And I think in that case, I would say that the fact that causal set theory can, if it could, let's assume for the sake of the argument that it can reproduce some small set of classical spacetimes in suitable limit, then I would say that it is a genuine prediction of the theory that, and a valid one at that, in the situation that closed time-like curves cannot be recovered. So in that sense, the set of spacetimes that we can or cannot recover, it in a sense counts as a prediction. Because it delineates those phenomena which are allowed by the classical GR from into two sets, those which are allowed by the fundamental theory and those which are not.
Okay. I guess I'll have to look at this more. It sounds interesting. Yeah, I guess I'm not sure what to say.
So that sense of prediction is I would think, a genuine sense of prediction, but that's not novel. We've seen in other cases of theory reduction or something like that before, in the sense that, for instance, statistical physics can maybe predict that there can be violation of the second law of thermodynamics. In a sense, that's a similar thing. That's a prediction of the fundamental theory. If it's true, then there should be some such thing, however unlikely it's a violation of the second law of thermodynamics. Similarly, in this case, the fundamental theory of quantum gravity may predict that, as a matter of fact, there's certain things, certain features of spacetimes according to general relativity that we're not going to see, or that we will see differently, or something like that. So in a sense, a fundamental theory could modify some of the assertions of the old theory, and as a matter of fact, it should in a way, right?
Yes.
Because it's supposed to give us a deeper, more correct understanding. But I think so in that sense, maybe we have predictions, but that doesn't really address the silly claims by string theorists that they can predict gravity, or things like that.
Sure. I was rather thinking about discrete approaches when I was asking this question. So I was thinking of it's hard to delineate predictions from expectations and consistency checks. So I think, for instance, the fact that causal dynamical triangulation people have something like 4-dimensional space, and that's more of a consistency check even for them. But maybe they would say that the genuine prediction of the theory is positive sign of cosmological constant, or something like that.
Okay.
But then, of course, that's not a testable prediction.
Yeah, I think there's definitely space here for it to be cast as a prediction. I guess. So yeah, I'll look into it. I guess my No, I won't say that. But I guess I want to know how much we've put in to get that out. Like, the reason we're getting these predictions are because we've gone from these things in our current theories that we've put in as ingredients to have that come out. Without like actual empirical ties to the world, it could be a bit dangerous. But again, without looking at it further, I don't know.
More questions here?
We have some more here.
Go ahead.
So towards the end, and I'm not sure I'm getting this correctly, but at some point towards the end you said we can have correspondence without GR or something like that?
I think probably without a limit.
Oh, without taking, I see, without there being a limit, I see. Okay, okay. Yeah, of course, yeah, I would agree with that. Okay, then I probably misheard you or mistyped as I was taking notes. In that case, I really just have a very minor question of sort of a historical interest in the paper by Crowther. What to me sounds like a distinction going back not to Popper and Lakatos, but really Reichenbach's distinction between context of discovery and the context of justification. Because when you explain the dual roles in which the correspondence principle, the dual roles the correspondence principle can have, namely one in a context of discovery, as it were, a theory of construction, and then one in the context of justification, post hoc. So does he actually use that distinction, or if not, do you think that would be a natural way to characterize what you're trying to get at?
I guess, let's find it. Yeah, he kind of doesn't really provide that argument very clearly. It's just kind of a quip, and then he is more interested in arguing against it by just saying that, clearly theory development is a continuing process, and develops his own philosophy of it. So I guess this is one of the points I want to think about more, because I'm not sure, I guess, without knowing kind of more history myself, kind of the relation between the two. But yeah, he doesn't properly explain that at all. And definitely not, even the way he attributes it, he's just like the legacy of Popper. So I don't even think he means Popper himself.
I was going to add there, for that sort of period, then N.R. Hansen is the person who kind of was most arguing for a kind of blurring of justification and a sort of, argued for an epistemically loaded context of discovery.
Yeah.
Which is kind of along the same lines here.
I think I'll look into it.
Maybe it has to do with correspondence as well, because I'm thinking the patterns of discovery, I think, actually does end with a discussion. Is it that book? Or maybe there's another book on quantum mechanics. I'll go, it's on my shelf, I'll go look later.
Yeah, I'd definitely like to read more on
I
that.
don't remember if he was thinking along these lines as well.
I mean, there's definitely an established literature in philosophy of science about the discovery justification distinction and to what extent it can be upheld, etc. So that might be fruitful for you to look at that.
Yeah, I think so.
Yeah. I mean, a lot of that literature has to do with sort of sociology of science and social factors, right? Rather than this kind of thing so much.
Right, that part may not be so useful for you.
I'm not doing that down, I'm just saying it doesn't seem to fit into what you have.
I understand, yes.
Can you say any more then about the bit you got to the end of my question about where the next work's going to be and what the principles are and what makes them, what makes something a principle and not a principle? We had a little discussion.
I don't know at the moment. It's just what I want to look at. I'm not, not sure of my own thoughts just yet.
Do you have a focus between sort of string theory or loop quantum gravity or causal set theory to answer these questions, or they're all kind of up for grabs?
Yeah, and it's tough because they're all kind of using different interpretations of it, and I'm kind of not sure in which direction to go to kind of look at the theories, these principles in isolation, or to start with them in the context of these different approaches. It's tough. I think I'll start even more generally and kind of look at the role of principles in theory change in the past, because they seem to be the thing that really carries it forward, again, and keeps these concrete links between old and new.
Okay. So also with the justification side of things, really in mind.
Yeah, like I'm wondering, like the fact that the principle is featured in successful theories, that kind of an empirical link. I think it's being used as one. But depending on, how it's interpreted in the different form, I'm really not sure. Yeah, lots of things to look at.
Yeah, for sure. No, as I say, I really like the way it was all framed.
Oh, thank you.
Go ahead.
Can I ask a specific question about the black hole thermodynamics and what's going on there? That's something I'm very interested in. And so what's your take on that? How does that exactly function in quantum gravity? I think on one of the pages of your slides you write that it serves as a target to reproduce. I think that's absolutely right. That's interestingly enough universally accepted as something that the quantum theory of gravity needs to reproduce. Does it? So in that sense, I guess it would be. It plays a role in the justificatory side of things. Mm-hmm. Does it also play a role as a heuristics in your view?
I think it kind of does both. Like the way we've arrived at it is by, from S to L, exploring our current theories and their interrelations and our limitations to come up with these, interesting novel results that are kind of explained by neither. So I think it's definitely something interesting that, I think it serves as the main kind of data that we should be linking back to. Definitely.
And why? So, one interesting aspect of this that you hinted at is that even though there's actually no empirical confirmation of Hawking radiation or anything like that, it's still pretty universally accepted as a. So there must be something that convinces physicists in the the heuristic play or interplay of different principles that we do there, that this particular way of putting them together gets something right.
Yeah. I think like it's almost a definition of quantum gravity that it should explain this. The way we expect it or want it to explain, these phenomena that arise at the intersection of our theories in this way. And I think the way it's kind of, it's quite a robust result. There are many different ways of arriving at it. Interesting in these condensed matter models as well. I find it fascinating that, this thermodynamics keeps appearing in all these different contexts. I think it shows that there is something going on there that we need to explain. And well, that's interesting. So maybe even if we don't get any empirical confirmation of quantum gravity, the theory, by having it just explain that, it might be enough. It might be, a non-empirical scientific theory, but does the job that we want it to do. So I think it's definitely interesting.
But presumably a semi-classical theory would be enough to, explain that.
Not in this kind of conceptually satisfying way. I think we want a new theory, something fundamental. But then, it's another question of what counts as a new theory and what's, a semi-classical approximation.
Thank you.
Thanks.
To follow that up a bit, the fact that you get sort of similar phenomena in different, very different contexts sort of suggests there's some underlying piece of math that's doing the kind of explanation that's occurring in these different cases. And presumably Chris is right that that piece of math is present there in the semi-classical case. So it's not the phenomenon itself that is leading us to want more, to want quantum gravity. It's our other kind of concerns that are driving us. Not the.
I think so.
The point you just made reminded me of another kind of question that I had. When you're thinking about the old and the new, and when you say these things about sort of conceptually satisfying, it sort of sounds a bit to me, and some of the other things you said sounds to me a bit as if you feel, well, when we've got the new theory, well, now we have a better handle on what the real stuff is, and we can see all the old stuff as, it's just appearances. It's not. It's kind of not very ontologically serious somehow. Do you feel that way? Because I guess I feel the other way. I kind of want a picture where there really can be levels of sort of, just because I found a more fundamental theory doesn't sort of undermine the ontology or the explanatory
definitely,
value
I'm
of
with
the
you
old
on
stuff.
that. Yeah.
Okay.
Yep.
So I'm kind of mishearing that.
Maybe I was devil's advocating myself, because I definitely, obviously I like this idea of emergence where each level kind of has its own reality, enough that we're entitled to believe in tables and chairs and electrons and gravity. Definitely. What was the
Okay, but on that sort of picture, then that sort of backs up when you say something like about the black hole radiation. Okay, semi-classical gravity is a perfectly legitimate level of the world, and so there are semi-classical black holes and semi-classical Hawking radiation, and there's nothing about this. This wanting a more fundamental theory doesn't sort of undermine the reality and explanatory value of any of that stuff. I mean, that's perfectly.
Yes.
Which sort of comes back to the other reason is, well, we know that isn't the complete story, and that's why we want something more fundamental.
Definitely. Yes, I definitely agree with that. So I think, again, what I argued in my thesis is that having firstly, I didn't think that we can get, a derivation in the strict sense of derivation of, macro physics from a micro theory, even a complete micro theory. I question the sense in which that is possible, even in principle, or making the claim that it's possible in principle. I don't think that has a great meaning. But even if we did kind of have this derivation, especially in effective field theory, it doesn't help you arrive at your appropriate degrees of freedom. So in that sense, I think the macro theory and our effective theories are more explanatory in a way that and correct in a way that the total theory of everything just can't be.
If I may, there's a sense in which semi-classical quantum gravity is philosophically, or as far as interpretation is concerned, arguably in a better position than most approaches to articulate the fundamental theory of quantum gravity, because at least we sort of think we understand what the theory is about, and what we do, at least to the extent to which we understand and can interpret quantum field theory. Now we do a minimal thing to it. We sort of have the background being curved. We couple this to dynamical equations, which is the most straightforward way. We have this averaging out of the quantum fields to that coupled to the classical space-time. So conceptually, it seems like a perfectly natural, thing to do. It's as satisfactory as doing quantum field theory on Minkowski spacetime or GR. It's sort of the next natural step. There are, of course, mathematical and technical problems in really doing that and getting everything solved, in a rigorous way, etc. But maybe it's not sort of conceptually that the theory is like.
Yeah, that's really interesting. I guess, two things. Why are we still seeking, a theory of quantum gravity? So kind of what else are we wanting it to do that these semi-classical theories don't or can't do? And it'd be interesting, how much of that is ideas of unification and beauty and all this stuff. Or I think it's interesting.
So what did you say, Chris?
So no, I mean, that's an excellent point. As a matter of fact, one attitude one could take would be to say, okay, no, what we need to find a satisfactory formulation of semi-classical quantum gravity, but once we have that, we've answered the demand for a quantum theory of gravity. There's really no need to go beyond that. Yes, this idea about gravity being subsumable in the same sort of framework that we use in particle physics, that was a bit misguided. There's no graviton. It's just that we need to couple a curved space-time background in the appropriate way to quantum fields, and done. And so what would be wrong with this attitude?
Using this kind of minimal definition of quantum gravity that I applied at the start, I mean, you're exactly right, that does fulfill it. What are all these extra things that we expect quantum gravity to do? Depends who you ask, right?
Yeah. But, I mean, for me, that is a very central question.
And I think kind of why we want it to do all these other things too. So the way I've been kind of leaning towards is for our human kind of, it makes us feel good, you know, to kind of have this nice picture, to feel as though we can explain everything.
I see. So I was going to say, the string theorists are going to say unification is what we want, and we get a more unified theory if we brought gravity in the same framework. And then they point to the successes of unification as well as respond to them.
So that would definitely be why I want to look at all these different principles that we expect to be important and that we want, and why. So, yeah, I'm looking forward to that.
Yes, we're very much looking forward to welcoming you in Geneva to work on this project as well.
Thanks very much.
But are there any more questions here? Otherwise, I think you guys all done?
That's it from our side.
Thank you very much.
Thank you.
And we'll be in touch, and have a good evening. And
Thank you.
again.